So let's see an example of that. It says, and this is a wonderful test question. Certainly on the test, you're going to have one that's a fraction where you get 0 over 0, where you have to factor and simplify and then evaluate the limit. Likewise, without a doubt on the test, you're going to have one of these where you're going to have a radical, you're going to plug it in, get 0 over 0, and you need to rationalize the numerator or denominator to get the answer. So without a doubt, this problem's on the test. Be careful with that. Let's try this. It says the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. So again, the first thing we always try to do is plug in the x value. So that'd be the square root of 0 plus 1 minus 1 all over 0, which gives us 0 over 0. Again, that's our indeterminate form. That does not mean that the limit doesn't exist. That only means we can't plug in the number directly. We have to do something else. So what are we going to do? Well, let's rewrite the problem here. So I have the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. The trick is to multiply by the conjugate. The conjugate in this case would be the square root of x plus 1, and then instead of minus 1, it would be plus 1. But if you do that to the numerator, you have to do the exact same thing to the denominator, because effectively all we're doing is multiplying by the number 1. What you do in the numerator, you have to do in the denominator. Okay? So now what are we going to do? Well, we're going to distribute. Let's first do square root of x plus 1 times the square root of x plus 1. So before I get too far ahead of myself, I'm going to write the limit as x approaches 0, because I need to keep that there. Now let's do the square root of x plus 1 times the square root of x plus 1. Well, that's the square root of x plus 1 squared, which is just x plus 1. Then we would have the outers, which would be the square root of x plus 1. The inners, which would be minus the square root of x plus 1. Notice those two terms cancel, and they always will as long as they're conjugates. Then we have the negative 1 times a positive 1. So that would be a minus 1. All of this is over x times, in parentheses, the square root of x plus 1 plus 1. Remember, never distribute out that denominator. Always leave your denominator in factored form, but you do want to clean up the numerator. So the square root of x plus 1 squared would be x plus 1. So here I have the limit as x approaches 0 of x plus 1 minus 1 all over x times the square root of x plus 1 plus 1 in parentheses. Now, I know you probably see two things happening right here. You probably see the 1's canceling and the x's simplifying. You cannot do both of those steps at once. Mathematically, you cannot simplify these x's until those 1's are gone. So you actually do need two steps here. I know you get sick of showing all your work, but you absolutely have to. Mathematically, you have to cancel those 1's first. I'm going to rewrite the problem now. The limit is x approaches 0 of x over x times the square root of x plus 1 in parentheses. Now, only now can I simplify those x's. You cannot do two steps at once. That is not mathematically accurate. So this is the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now that I've rationalized the numerator, I can actually plug in the number 0. Since I've plugged in the number 0, notice I'm not going to write that limit as x approaches 0 anymore. I'm actually plugging in 0, so I get rid of that notation. I have 1 over the square root of 0 plus 1 plus 1. Square root of, well, 0 plus 1 is 1. Square root of 1 is 1. 1 plus 1 is 2. I'm getting a total value of 1/2. Okay? So that's what I'm getting when I do this problem. When I originally plugged it in, I got 0 over 0. I rationalized the denominator. After rationalizing the denominator and plugging it in, I was able to get the value of 1/2. So what could I do at this point in time? I could take literally the 30 seconds or less that it takes to plug this into my table feature of my calculator to verify my answer. Highly, highly recommend doing that. Hit table, type in the square root of x plus 1 minus 1 all over x. You're going to plug in numbers to the left of 0, like negative 0.1, negative 0.01, negative 0.001. You're going to plug in numbers to the right of 0, like 0.1, 0.01, and 0.001. And you should notice all of those values getting closer to 1/2. So what's the last thing that we have in this section? A really, really cool theorem. to use. One of my favorite theorems when I was in a calculus course, undergrad calculus courses, it's called the squeeze theorem. And what's the idea? The idea is if I have this function f of x that I don't know, that I can't find the limit for, I can't do something nice like factoring and simplifying, I can't do something nice like, I don't know, rationalizing the numerator or rationalizing the denominator, I don't have any techniques other than using a dang chart or graph, what's something I can do? Well, here's the idea. If I can find a function g of x that's always bigger than f of x, and I can find a function h of x that's always lower than f of x, and g and h both go to the same number. So here's at x equals c, I'm looking at this point right here, I'm looking at evaluating that limit. The limit as x goes to c of g, the higher function, and the limit as x goes to c of h, the lower function. If those are the same thing and f is stuck in between them, then that must be the limit right there. That must be the limit of f. So that's the idea. Find a function bigger than it, find a function lower than it, and if the bigger and lower function agree, then that middle function f also has to agree. It gets squeezed in there, and that's why they call it the squeeze theorem. And that's what you see right here. It says if h of x is less than or equal to f of x is less than or equal to g of x. So h of x is the smaller function, g of x is the bigger function. For all x in an open interval containing c, except possibly at c. So remember, it doesn't matter what happens at c, only near c. And if the limit as x approaches c of h of x equals L equals the limit as x approaches c of g of x. So if the limit of the lower function and the limit of the higher function are the same, then the limit of f of x, that middle function, has to exist and it has to be that same value. So again, if the upper function and the lower function's limits agree, then the limit of that middle function has to agree as well. That's the squeeze theorem.